So we're going to be learning about impulse and momentum today. So if you first think about how you want to push a bowling ball to get it to go fast, there's a couple different ways to do it. So first of all, we need to think about what kind of force do we want to use and how much time do we need to push it. So if I want to make the bowling ball go fast, I could apply a big force for a big or a small amount of time, but the main thing would be that, to get it to go fast, I could apply a big force. The other option is that I could push on it for a long amount of time with a relatively small force. And of course, I could push it with a big force with lots of time to get it to go even faster. But the idea being, if I want to get this going fast, I can either push with a big force or a lot of time. So, impulse is this idea of pushing it to make something move. And impulse, the letter for the variable is capital J, and impulse is force times time. If we're going to write it in equation, it's J is equal to F times T. And the units are newtons times seconds. So just like the units for force is newtons, the unit for time is seconds. And so that's where we're getting newtons times seconds. And sometimes you just see it as NS. So if you want to change the velocity of an object, you're going to apply an impulse. And the bigger the impulse, the bigger the change in velocity. But exactly how much it'll change, we'll get to that next. So either way, it's not just about force and it's not just about time. It is about both. So if we want to make something speed up, it's not just a big force, but we also need to push on it for a significant amount of time. Otherwise, it's not going to speed up as much. So momentum. I like to define momentum as motion oomph. It's kind of a silly definition, but that's how I define it. And so if you just think about what has more momentum, an elephant on a scooter going slow or an identical elephant on a scooter going fast, you're like, well, the one that's going faster has more momentum. It's like more motion oomph of whatever you want to call it. So that means that if I want more momentum, I need to go faster. But if I think about it also in terms of I have two different things, I have an elephant going a certain speed and I have a mouse going the same speed. Who has more momentum now? Well, the elephant. The elephant has more momentum because it has more mass. So if I want more momentum, it could be because there's more mass, or it could be because there's more velocity, or both. So momentum is lowercase p. And to calculate momentum, it's just your mass times velocity. And so if you write it as an equation, it's m times v. And if we want to talk about the units for momentum, we just need to use the units for mass, which is kilograms, times the units for velocity, which is meters per second. And so we get the units of kilograms times meters per second. That's literally it. There's no special units at all for momentum. It's just kilograms times meters per second. And if you ever need to find the total momentum of a system, like you have multiple things, all you have to do is add the momentums together. So find the different momentums and just add them together to get the total. So we have a brown bear named Gorilla that is 7 years old, and he's run a distance of 25 meters, has a mass of 100 kilograms, and is running with a velocity of 5 meters per second. What is the momentum of Gorilla? So momentum is mass times velocity. So I've given you extra numbers. You only need the numbers for mass and velocity. So we're going to do the mass, which is 100 kilograms, times the velocity, which is 5 meters per second. And I get a momentum of 500 kilograms times meters per second. But how are momentum and impulse related? Well, if you think about it, if I shove that bowling ball with my broom and I apply a force for a certain amount of time, it's going to make the bowling ball speed up by a certain amount. Likewise, if I use the same broom, apply the same force for the same amount of time, and then push on a basketball, the basketball is going to end up going a lot faster because it has a lot less mass. So how are they specifically related? Well, it comes down to this, that the more force or more time applying the force means that you're going to have a bigger change in momentum, and that change in momentum is then going to be equal to your force times time. So that means my change in momentum is equal to force times time. This being change in momentum is mass times how much your velocity changes, and force times time is your impulse. So you have, now here it says change in momentum, and here it's change in velocity. And the reason for that is in the examples that you guys will be doing in physics, the mass of the object's not going to change. It's just the speed that's changing. So if your car gets on the freeway and you want to speed up, the mass of your car is not going to get significantly heavier or significantly lighter as you start to speed up or slow down. Versus, like, if you were going to launch a rocket like SpaceX, for example, there's a significant amount of fuel that is used up during the flight. And so then your mass would be changing. But we're not going to worry about that. Not in this class. So let's do an example. So you have an 8-kilogram bowling ball is rolling towards you at 10 meters per second, and you want to make it stop. You are trying to decide how to stop it. So there's two different ways. One, you can put your foot on top of the ball to slow it down in 4 seconds. And you're going to calculate how much force you need to apply to make it stop in 4 seconds. So my mass is 8 right here. My change in velocity is, let's see, I was going at 10 meters per second, and now I want it to stop. So that change in velocity is going to be 10. So I was going 10, now I'm going 0. So maybe I say times negative 10 then. And then this is going to be equal to my force, which I don't know, that's what I'm trying to find, force, times time. And for this one, it's 4 seconds. So we're going to go times 4. All right, so if I write this out, I go 8 times negative 10 is negative 80, and that's going to be equal to force times 4. So because it's force times 4, I do the opposite. I'm going to divide both sides by 4, and I get an answer of my force is equal to negative 20 newtons. Cool. All right, so then let's do the same thing again. But now we're going to use method 2. So method 2, it says you put your foot in front of the ball and kick it to slow it down in 0.5 seconds. How much force do you need to apply to make it stop in 0.5 seconds? So again, my mass is 8. My time now is 0.5. I'm still trying to find my force. And my velocity is still, I went from 10 meters per second to stop. So that's going to be negative 10. So I get 80 is equal to 0.5 F. Divide both sides by 0.5. And I get 160. So if I want to think about this, here I have a big amount of time with a small force, or I can have a small amount of time with a big force. Now, this is important for car crash safety because if we want to experience a smaller force, that means that then we're less likely to get injured. And if we're less likely to get injured, that's a good thing. So we want smaller forces. So if we're going to have a smaller force, that means we need more time to stop. And so most of the safety features in a car are going to be just that. How do we make you stop over more time? So here we have a baseball getting hit with a bat. And if you notice right when the ball is starting to be in contact with the bat, it's not very compressed because you're not pushing very hard. And that's what this part means right here. This is a small force because it's not very high up. And then when the ball is getting squished the most, that's right here. That's when the ball has a really big force. So like this would be your really big force that it's getting hit with. And that makes sense because it takes a lot of force for the ball to get squished like you see in this video. And so this is a really big force up here. And then down here, we're back to small forces. And so this is how it actually works in terms of like as time goes by, it starts with a little force when you just start touching it, and then the force is really big when the ball is all the way squished, and then it gets small again as the ball leaves the bat. Now, this same thing is going to happen when we talk about car crashes. So here we have two different cars, same change in velocity, same mass of the car, which means they have the same change in momentum. Okay, so the momentum is the same. So my change in momentum is the same. Now, that means that my impulse is going to be the same. And impulse is force times time, but the force keeps changing on us. So in reality, what happens is the area of these two graphs is the same, but the difference is that the maximum force here is relatively small, whereas the maximum force for this one's really high. And the reason for that is if we're trying to make the force small, we need to have more time. Look how much time it took for this car to stop when it crashes into the hay. Versus this one, it's only a very small amount of time to stop. And if you only are stopping and applying a force for a very small amount of time, that means you need a really big force to make you stop in a small amount of time. So by crashing into the hay bale, it takes more time to stop. So then why would a padded dashboard be better in a car crash? I want you to think about this and think specifically, what are the things we've talked about? We've talked about force, we've talked about time, we've talked about mass, and we've talked about velocity. So of these things, if you crash into a dashboard, the squishiness is going to mean that it takes you more time to stop. And if there's more time to stop, then that means that the force is going to be less because the time that it takes is more. So you have to stop either way. You weigh the same either way, but the force will be less if the time it takes you to stop is more. All right, so now you get to apply it. Good luck, and let me know if you have any questions.